So in the introductory video for theory of computation, we did mention that we'll also learn some concepts in linguistics and language, right? So we'll also learn some concepts in linguistics and language as part of theory of computation, because there's a very deep underlying connection between something called as formal languages, right? So there is this whole concept called as formal languages, which are nothing but mathematical and rigorous definition of what a language is in the first place, right? So this is again, these are concepts from linguistics itself. And as we progress through the course, you will understand how this concept of formal languages is very deeply tied. It's extremely deeply tied to the concept of a machine or an automata, right? So we discussed about these terms a while ago, right? In a very introductory video. So the concept of grammars, again, in formal languages, we'll learn a bunch of terms in this video. I'll simply define these terms, but the deep underlying connection between the theory of computation systems like machines and automata to formal languages, we'll understand that as we progress through the course, okay? For every model, or so for every mathematical model, or for every automata or machine that we learn of, there is a formal language associated with it, okay? That we will learn it as we progress through the course. Right now, let me introduce you to some simple terms, and I'll try to define these terms from the mathematical concepts that we learned or that we recapped a while ago. So for example, the very first concept that we can learn of is the concept of an alphabet. Okay, again, some of these terms are what you would use in English or in Hindi or in Telugu or in any language, any spoken language. So what are alphabets? So if you look at it, we do encounter a lot of alphabets, right? In English, again, alphabets are often represented using this capital sigma. So sigma English, what are all the alphabets that I have? Capital A, capital B up to capital Z or capital Z, and small case a up to small case z. These are the alphabets that we typically use in English, right? Similarly, I can have binary alphabet also. So if I have to write a binary strings, okay, the way computer code is written, so it's only made of zeros and ones. So the binary alphabet is just zeros and ones, right? Similarly, if I have to represent numbers in decimal, right? What are all the symbols that I use? I use 0, 1, 2 up to 9, and I also use a dot, right? To represent things like 2.34 or 2.56. So my decimal numbers themselves, right? These are all the symbols that I use to represent decimal numbers. Similarly, if you were to represent something in Hindi, right, which is a very popular language in North India, right? So we use alphabets like this: A, E, E, right? So we use the bunch of alphabets here. Similarly, if you look at alphabets in my mother tongue, which is Telugu, right? We have alphabets very similar to Hindi: A, E, E, a bunch of alphabets like this. Most modern programming languages, or not just programming languages, I'm sorry, most spoken languages, actually there are some spoken languages which don't have the written script, but a big chunk of spoken languages like Telugu, Hindi, English, they have symbols which we use to represent, which we use to write a language in, right? So similarly, binary is the computational language. So you can think of alphabet. What is an alphabet? Very simple. Alphabet is a finite set of symbols. Very simple definition. It's a finite set of symbols. That's all there is, right? Why is it has to be finite? You can't have infinite number of symbols that you're using. It has to be a finite set. And there are symbols, of course, each symbol has a specific meaning, right? For example, this is to be pronounced as A in Telugu. This is to be pronounced as E in Hindi. This is the binary 0, which means in the logic circuits, this is equal to 0. So, or off, this is on, right? In decimal, you have 0 to 9 and a decimal point. So each of these symbols have special meanings based on the context. But mathematically speaking, from a formal languages perspective, alphabet is simply a finite set of symbols. It has to be finite. Let's not forget that. And alphabets are typically represented using the capital sigma. Okay. Now there is also something called as an empty language. An empty alphabet. I'm sorry. So there is also something called as an empty alphabet in formal languages. The empty alphabet basically means the empty set. An empty set is also a finite set. So which means there is an alphabet like this, which we often write it as sigma empty, which is equal to an empty set, which has no symbols. This is also an alphabet because 0 is also a finite number, right? So these are examples of what alphabets are, and I'll try to connect some of the concepts that we're learning right now to spoken languages or binary language, okay? Like English or binary language, because many of you may not, only some of you may know Telugu, some of you may know Hindi. I'll avoid using them, but I'll use lots of binary symbols. I'll use a lot of English symbols. I'll use a lot of decimal symbols also, right? So this is what an alphabet is. Very simple. From a mathematical viewpoint, it's a finite set of symbols. That's all there is, right? So the next concept after alphabets is the concept of a string. The concept of a string or the concept of a word, right? We use the concept of a word in English, right? So what is a word? So if you think, let's look at examples, right? Like, for example, if I have ABC, this is a word, right? It's a word if you think about it. Or if I have 01010101, this is also a word, right? Or if you have applied, right? This is also a word in English, right? Similarly, 1, 2, 3, 4, 5. This is a valid word. If you look at this alphabet, if you look at the decimal alphabet, this is a valid word. Similarly, I can write words in other alphabets also. I can write words in Telugu. I can write words in Hindi. Most languages which have a script, right, which I can write, right, I can compose strings or words. Now, what is a string or a word? Formally speaking, it's a finite sequence. Look at this. It's a finite sequence. We saw what a sequence is, right? We saw what a sequence is in the previous video. So a string or a word is a finite sequence of alphabets. So we saw what an alphabet is, right? We saw what an alphabet is. An alphabet is basically a finite set of symbols. That's all. A string is a finite sequence of alphabets. It has to be finite. It can't be infinite. That's very, very important, right? So then, of course, there are some very simple concepts called the length of a string. Obviously, the length is basically the number of alphabets, right? The number of alphabets in the string, the number of alphabets in the string or the word. Again, the word string and word are used interchangeably. For example, the length of this is 3. The length of this is 1, 2, 3, 4, 5, 6, 7, 8. The length of this is 1, 2, 3, 4, 5, 6. Because dot is also in this alphabet, dot is also a symbol, right? So hence I have 6. This string length is 6, right? So can I have an empty string now? Can I have an empty string? Yes, you can always have an empty string. What is an empty string? Empty string basically implies length equals to 0. So to represent empty strings, there are special symbols that are used. Typically, we use the symbol epsilon to represent an empty string. But in some books and articles, you may also encounter this capital inverted V or lambda. You will also encounter these symbols for an empty string. The most popular symbol being epsilon to represent an empty string, right? So in other words, if you think about this, the length of an empty string. Again, string is also a sequence. Look at this. A string or a word is a sequence to start with. Okay, the length of this equals to 0. And if I add or if I concatenate, we know what is concatenation of strings, right? Suppose if I have ABC as a string and if I have DEF as a string, I can concatenate both of them to create a longer string. Okay, this is what we have studied. Concatenation is something that you probably studied in C programming language, right? So concatenation of strings. So if I concatenate E with any string S, this is equal to concatenating S with the empty string, which is equal to S itself. So concatenating any string, again, in some cases, people also place the dot here to represent that I'm concatenating them. So if you concatenate an empty string before or after any string, you'll get another string, right? So imagine if I have an empty language. Look at this. If I have an empty language, sorry, if I have a empty alphabet, okay, not a language. Okay, in formal languages, again, there is a definition of what a language is also. In a little while, we'll see that, right? So if I have an empty alphabet, this has no strings, right? An empty alphabet, you can't construct any string out of this. Okay. So now similarly, there is this concept called as, suppose imagine if I have an alphabet sigma. So this is called as sigma star. Okay. So sigma star is defined as the set of all the strings, set of all strings, including empty strings. Okay. Including empty strings. including empty strings, the set of all strings that you can construct, all strings formed using the symbols in sigma, right? So you're given an alphabet sigma star, or the alphabet star is a set of all strings that you can form using the symbols that you have in your alphabet, right? I hope this is clear, right? This is a big set. If you think about it, if my sigma is sigma binary, right? This is the set of all strings or all words that I can form using binary digits, and that will be infinitely many here, right? So there will be many such strings. Okay, so I hope you got a sense of what sigma star is, because we'll use this to define what a language is. Okay, what is a language now? What is a language? In a mathematical sense, what is a language? Okay, a language is a subset of sigma star. Remember, sigma star is a set of all strings that you can form. And what is a string? String is a finite sequence of alphabets, right? So amongst all the strings, a subset of strings forms the language, right? For example, if you take any spoken language like English, not every string, look at this. If you take English as an example, right? Look at English, right? This is the easiest example to grasp this concept. What all symbols do you have? Capital A to capital Z, small a to small z. These are the symbols that you have. Now, using those symbols, I can create many strings. Of all the strings, only a subset of those strings form the English language, right? For example, in English language, you don't have a string like this. This is not a valid string in English language. While in English language, let's say home is a valid string, right? Work is a valid string. X, Y, W is not a valid string. So a language is a subset of sigma star. Okay, of all the strings that you can form, a subset of them constitute the language. Okay, so again, this is a formal definition of what a language is. Remember that a language is a set at its very core. We cannot forget that. Because a language is a subset, it is also a set. Language is a set, which means we can perform operations like union, intersection, right? These are all operations on sets, intersection and set difference. We'll also learn of other operations that we'll perform on languages a little later. Okay, so typically people use the symbol L to represent a language, right? A language at its very core is a subset of all the strings that can be formed using an alphabet. Remember, to define a language, you need an alphabet. Without an alphabet, you can't do anything. First, you have alphabets. Based on alphabets, we create strings. Then we have the set of all the strings that can be formed. Now, from that set of all the strings that can be formed, we create a subset and call it a language. Now, obviously, just for completeness sake, what is a grammar? What is a grammar? What does the English grammar tell us? English grammar is basically, think about it from the perspective of English, right? There are a bunch of strings or words which are valid in English. Now, what does grammar tell us? Grammar is a set of rules. Grammar is a set of rules to produce valid strings. To produce valid strings. Right? To produce valid strings in a formal language, obviously. In a formal language. Right? So just like in the case of English, see, this word is a valid word, this word is a valid word. Now, how do I combine these words to construct, again, in English itself, again, just to be clear here, English also has space. English also has these symbols like comma, like exclamation. English has many of these special symbols also as part of English alphabet, right? Now, using those alphabets, I can construct sentences. Remember, a sentence is also a string. A sentence is also a string, if you think about it. If you consider space, exclamation, comma, all of these as part of your alphabet, then a sentence in English is also a string or a word, right? So a grammar gives you a set of rules to produce valid strings. Now we will learn of how to actually represent these rules mathematically. Okay, we'll learn that little later. Okay, so we will learn more about grammars. Again, grammars are a very important concept in formal languages. Okay, so grammar basically gives us a bunch of rules on how to produce valid strings in a formal language. How do we define these rules? How do we write these rules? we'll learn of all this stuff little later. Okay, but to just introduce you to this terminology, English is a very easy thing. Again, in practice, in formal languages, as far as theory of computation is concerned, we will not be only worried about English language. Okay, I don't care. Again, that's what mathematics enables us to do. I don't care whether it's English, Hindi, Telugu, binary language, decimal language, or decimal alphabet. I don't care. Okay, as long as you give me a set of symbols, I can define an alphabet, I can define a string, I can define a language, I can also define a grammar. Okay, we'll learn about grammars little later. Okay, because how do you write these rules mathematically is something that we'll learn of as we progress through the course. But just wanted to introduce you to these terms here. Obviously, there are some more very simple concepts like a substring. Right? We know what a substring is, right? So if you take this, right? Imagine if this is a word that I have. Imagine if this is a word that I have. This is a substring. Right? This is a substring. Now, how do you define a substring formally? Okay. So given sigma, given an alphabet, U is a substring. U is a substring. Given an alphabet, U is a substring of V if there exists X, U, Y, which is equal to V. Again, here, U, X, Y, V. All of them belong to sigma star. Okay. So, what is sigma? Sigma is the alphabet. U is a string. V is a string. X is a string. Y is a string. Right? All of them are strings. And how do you say they're strings? Because they belong to the set of all possible strings that you can construct from sigma. Right? Then you say U is a substring. Again, what does this mean? This means, see, we said, let's assume this is U. Okay. This whole thing is V. This whole thing is V. We say U is a substring of V if there exists X. So this is my X. This is my Y. If X, U, Y equals to V. If there exist strings like strings X and Y. Again, these can be empty strings. X and Y can be empty strings, right? But if there exist strings X and Y, which if you place U in between, if you get V, which means U is a substring. Okay, for example, look at this. Look at this example. EDE. Is this a substring now? Yes. If this is my U, okay, this is my X. What about my, this is my Y, I'm sorry. This is my string Y. This is my string Y. This is my string X. My string X is an empty string, which means this is epsilon here, right? So this is now a substring of the full string. What is my full string? This is my full string. This is my full string V. So U is a substring of V because there exists X, which could be empty, and there exists Y. Both of them are valid strings in this alphabet, such that if I sandwich U between X and Y, I get V. Okay, that's what is the definition of a substring. Very simple concepts if you think about it, right? Similarly, you can define the concept of a prefix also. Again, look at how we are trying to define these concepts, not very loosely, but very formally, in a very mathematical sense. Okay, and that this mathematical rigor or this mathematical clarity is super important in theory of computation, because we'll try to understand everything as mathematically as possible. This concept of substring is something that you probably learned in your C programming days, but here we are trying to define that in a very, very formal sense, using concepts like sets and sequences and alphabets and languages and strings. Again, the definition of what a string is itself is very formal here. String is a finite sequence of alphabets. We know what a sequence is in mathematics. We know what an alphabet is. An alphabet is a set. It's a finite set. So see how we are trying to define these terms from a very formal mathematical sense. And that is important in theory of computation, because we want to be as precise as possible. Now, what is the concept of a prefix? Imagine, take this string, right? Take this string here. Okay, this is a string in my binary alphabet, right? My alphabet now is binary. Now, when can I say that this is a string, or this is a prefix to the big? So let's call this as V. Okay, let's call this as U. So U is a prefix. U is a prefix. U is a prefix of V if there exists X. Okay, there exists X such that Ux equals to V. And again, obviously, U, X and V, all of them belong to sigma star. right? Look at how I'm defining it very formally. Okay, look at this, u, v and x are strings which are constructed using sigma, which means they are elements of sigma star, right? Now using them, I'm defining a prefix to be such that if you have prefix followed by, again, x can be empty string here, x can be empty string, because empty string is also an element of the alphabet star or sigma star in this case, right? So x can be empty string. Now here x is referred to as the suffix. In this case, x is referred to as the suffix, u is referred to as the prefix. This is how you define concepts like prefix and suffix in a mathematically rigorous fashion, right? Similarly, there are other concepts also. There is a concept of concatenation of strings, right? There is a concept of concatenation of strings. And what is a concatenation of two strings? Very simple. If u is a string and v is a string, you concatenate both of them such that u and v belong to sigma star, right? So u followed by v. Look at this. This sequence, again, a string is a sequence where you are concatenating this sequence with this sequence. So for example, if u equals to abc, v equals to xyz, then what is uv? uv is nothing but abc xyz, right? So you're concatenating these two sequences to create a new sequence. Okay, that's what is called concatenation of strings, right? So this, again, what we're introducing here are the very basic definitions. Think of it as a basic introductory definitions in formal languages or linguistics. Again, linguistics is a much broader subject. Okay, formal languages is the mathematical topic which is a subpart of linguistics that we'll study. Linguistics is a study of language itself, which is a much broader topic. Formal languages, so from now onwards, I'll not refer to the word linguistics, I'll use the word formal language or language. Whenever I say language from now onwards, it means a formal language. Okay, so a formal language is what we will study in theory of computation, and we'll see a deep relationship between formal languages and machines or models or automata that we'll learn of later. The core concepts here are alphabets, strings, and languages and grammars, right? Of course, substring, prefix, suffix, concatenation, these are fairly simple concepts to absorb.